In addition to our logical axioms, we also need to add primary rules of inference to develop our logical system. So we are going to add two rules of inference to our logical system that will help us to form new mathematical truths from our axioms or our special axioms or special assumptions. So we have the following two rules of inference. The first one is called equanimity, and the second one is called the Leibniz rule. And both of these rules of inference, you will see, are also common sense assumptions that we are making. So you'll see that in order to develop mathematical truths the way we want to see them, we will take for granted that these two things must be true. So equanimity says that if we know that A is true, and we know that A is equivalent to B, then we can conclude that B is also true, right? So by our use or our understanding of equivalence, this rule of inference should hold. So if A is true and A is equivalent to B, then we know that B is true based on the semantics that we have defined in terms of equivalence. So you will see that the numerator in the rule of inference shows the premises or hypotheses or assumptions that we are taking to be true, and the denominator shows the conclusion or result of the rule. So as I said, if we have A and we have A is equivalent to B, so if we assume that both A and A equivalent to B are true, then we can conclude that B is also true in this rule of inference equanimity. The second one sort of establishes how to understand substitution and how substitution behaves. So what does Leibniz say? It says that if we know that A is equivalent to B, so one well-formed formula is equivalent to another, then by substituting either of these formula into another well-formed formula, we should get equivalent statements. So if C prime is a well-formed formula we get by substituting A into C, and C double prime is a well-formed formula we get by substituting B into C, then we have that C prime is equivalent to C double prime, right? So if we substitute equivalent formula into the same well-formed formula in the same place, then we should get equivalent formula. So that's what Leibniz tells us. So it tells us that equivalence is preserved over substitution. So as I mentioned before, this first rule is called the rule of equanimity, and we'll denote it by EQN. And the second rule is called the Leibniz rule, and we'll denote it by LEIB, or lab. Okay, so this brings us finally to be able to define what a theorem calculation is or what a proof is. So we're going to define theorem calculations or gamma proofs. So recall, gamma is our set of assumptions that we have. So let gamma be a given set of formulae, our assumptions. So gamma could be empty or could consist of two or finitely many well-formed formulae. We're going to take those to be our assumptions. We're going to take those to be true and use them to develop new truths. So a theorem calculation or proof from gamma is any finite ordered sequence of formulae that can be written following these rules. So a theorem calculation or gamma proof is a sequence of well-formed formulae that follow the following rules. So just like a formula calculation follows steps or rules, a theorem calculation follows those same rules. So it's very similar. So the first is that we may write a formula from lambda or gamma at any step. So we can write an axiom, any of our logical axioms, at any point during our theorem calculation, and we can write any of the special axioms or our assumptions from gamma at any step. And remember, gamma is not fixed, so it depends on the particular situation or the particular theorem we're wanting to calculate or prove. So at any step we will write any axioms or any special axioms that exist within our particular instance. And finally, we may write the denominator of an instance of an inference rule, provided all formulae in the numerator of that same instance have been written in a previous step. So, for example, we can apply EQN as long as A and A equivalent to B appear at some step of our theorem calculation. Or we can apply the Leibniz rule so long as A equivalent to B occurs at a previous step of our theorem calculation. Okay, and that brings us to the definition of a theorem.